कल और परसों कर लेते हैं कहीं चक्कर ही नहीं रहेगा।
बिल्कुल बिल्कुल हाँ सर इसकी कल से
मंडे वनडे तुम्हारे तो फोन टीएस पर रहेंगे
हाँ
खाना ही
हाँ
तो
बिल्कुल।
मैडम के रहते रहते।
हम्म, हाँ मैम के रहते रहते हो जाएगा तो सही है। मैम बहुत कोऑपरेटिव है।
हाँ कोऑपरेटिव में पता नहीं। हेलो, गुड मॉर्निंग all of you. We welcome you in the fourth day our session on the basics of image processing with application. Am I audible? Okay, thank you. Pravesh, Saujanya, Aditya. So, if you have any questions before starting the today's sessions, because it's regarding the basics, how are you finding the things? Any difficulty or anything which you have learned new, want to share with others? Just within 5 minutes, you can have the last lecture. Please write your questions so that it can be understood by everyone. Okay. So how are you finding it course? Moderate, difficult, easy? Because your feedback will actually help us to decide moderate, fine. Hands-on session, okay, Saujanya. Hands-on session actually we had been planning to do, but the main problem is that while online it becomes very difficult because some people while running the program they had the some issue, they are not able to debug. So then what happen? It is very difficult to actually bring everyone at the same pace. That was the only problem that I did not design actually the any hands-on session in this workshop. Can you have the PDF so we are not able to open at our site? Definitely. Do you want to discuss research paper? If you want research paper, definitely. I really will be very happy. But only I want to see that how many. In the end, actually, we have the plan that when the application part, image processing application will be there. Then we will discuss. So Google Colab, Jupyter Notebook, definitely see what we will do. We'll provide you some program where you can write the thing, where you can run the thing, and then you can try it. That we can do. Anything more, anything which you want. That thing is noted that someday we will capture the C screen that how the Google Colab, etc. So how many have already worked upon the Google Colab or Jupyter Notebook apart from Saujanya, like Parvez. Parvez, we are done. Very good. It is very actually simple one. It's not at all a problem. That's why these fields are very popular. And then the best thing here, all these things are open source. Since they are open source, so we don't find difficulty. Very good. So for ML algorithms, we have done it. So definitely we will do it. Any other would like to share that what who have done the programming in Google Colab, Jupyter Notebook, other participants. So no problem. So we will do it. Anything more? Any? You are finding course interesting. You reading it? MCA project. And I couldn't get it. MCA. What was the MCA? Any mathematics and computing applications. Thank you. See, interesting. It's definitely your participation also motivated me to go through these things. Insurance cost prediction. Yes, yes. Actually, these are all the ML part. Machine learning algorithms are there where you apply the regression, etc. These are the popular basic machine learning algorithms that people do it. So definitely, so I noted down. So we will go through it. We, what we will do, actually, one minor change in the session that on Sunday, actually, these people where we are conducting these sessions, that uh, remains closed. So what we are doing, we can stretch the 2 hour session tomorrow and 2 hour session day after tomorrow. So on the Friday and Saturday. So that we can do. Tomorrow session will be, we can have session from 10 to 1, right? And in the evening, then we can have from the 3 to 6. In the same way on the Saturday also that we can do. 10 to 1 and 3 to 6 on the 19th as well as 20. So you Sunday is free. Don't have any class on the Sunday. So we started. This is great. Whatever your research is there, you can definitely, you can always ask feel free to ask the problem. Again, my commitment is that even I may not able to answer some problems quickly, but I will definitely able to answer the questions at the end of this our workshop, because it would only my concern is that whatever session you are joining, you are able to get some meaningful advantage of it in you, so that in permanent advantage apart from the certificate and external the achievement. So now we coming to the part, just see recalling the things earlier. See, we started basically now in the image processing, we started from the histogram part. The best part of histogram is that it's very simple. It's very simple to execute, very simple to count the things, etc. Then we took up the different type of cases in the histogram where we took basically the histogram stretching. Thereafter, we took the case of the histogram equalization. Then we took up the case of the adaptive histogram equalization. There we basically made the different parts. We divided the image into the different parts locally. Then we basically took up the clipping also, Clay, uh, clip adaptive histogram equalization based upon the different patterns. But overall, see what did we observe that histogram has some basic limitation. Where its limitation, if you see it, we discussed it yesterday, that neighboring, absolutely. That everything is fine, these two figures, if you draw the histogram, it will be the same. And when it will be the same, so same pattern will be there. Then the problem is there, that neighborhood. See, this figure is different, this figure is different, that neighborhood is there. So this neighborhood is not taken care by the histogram. Then the another approach has come into the picture, that is basically the filtering and what we call the spatial filtering. The spatial filtering, see what does this spatial refers to? Spatial refers to basically the location of the pixel. What location of the pixel? Can we see any image? See this one. See, for example, see, this is basically the spatial location. This is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8, this is 9. So these are the all basically the locations of the different pixels. Since they directly work upon based upon these locations. So what do we say? And even see if you see the neighborhood itself is basically based upon the location. So now the directly this location part will become very important. So now what did we observe, that the thing which is basically used, the or object which is basically used in this main object which is used in spatial filtering, that is mask. What do we mean by the mask? Mask is basically, as we have already seen it, this is basically the mask here. This figure, for example, this 3 by 3 block, that is basically the mask. Or it is a filter. Both the things are the exactly same. Mask is basically initial thing which is used to do the filtering. Some people also, in some books, it is referred as a filter. So now, what do we do? Now we will observe it. For example, this is 3 by 3. This mask is a very popular one. So what do we do? This central element, remember, as we noted down here, that this is specific center pixel. Remember, every word is very important. So this one. This specific center pixel is basically overlaps with the pixel value where it works upon. What happens? For example, if I want to work upon any pixel which is lying here, then what I do, I put this central pixel, specific center pixel of the mask on that pixel of the image. Once it is put there, the other values of the mask also align with the another value in the neighborhood. So what do we do? So we multiply, etc. That we will see. That what do we do? So this way the things occur. This way the neighborhood is taken care by the mask. Now we're going through it. Spatial filter basically has a two type: linear spatial, non-linear spatial. See, what do you know? Linear. See, linear means basically here the values are basically based upon the directly on the name. Means if we consider the value, they are all basically we say based upon the addition, multiplication. But in the non-linear part, see this, if we arrange the values, it is not simply upon the addition or the division, etc. It is based upon the some another mechanism, which is basically non-linear in nature. That's why we differentiate it that linear and another is non-linear. So in the very popular and very simple filter, basically the mean filter. Even so, you would have observed that when you scan the image, even in your mobile, when you use it, different type of filters are there. For example, you want to take the they will give you the option whether you want to take the original image or whether you want to take the dark image or whether you want to take the light image, etc. These are there. So how you are able to do? Again, using these filters. Different, they will basically have different type of function is called. So what we calling here, so averaging filters. In averaging filters, see what is the effect. Whenever you are discussing any filter or any image processing operation in our mind, what should be there, that what is its impact on the image. So when we take out basically the average filter, in average filter is basically when you average out, then it is basically a image becomes blurred overall generally. In the weighted averaging filter, what happens? Here the pixels are multiplied by the different coefficients and central pixel multiplied by a higher value than average filter. So if you want to put the more emphasis on some pixels, then you use the weighted averaging filter. Correlation. So two things are very important in this spatial filtering. One is basically the correlation and convolution. What is correlation and convolution? Correlation and convolution are basically the methods that how does the mask operate upon those original pixels of the image. What happens in the correlation part? Mask values are directly multiplied with the image pixel. What happens in the convolution? In convolution, as it has been shown here, that the mask is first flipped. The mask is basically first flipped both horizontally and vertically, and thereafter you multiply. We will see what do you mean by flipping horizontally and vertically in our next slide. Now, question I see, where do we use basically the correlation? The correlation is basically used when you want to find out the pattern matching, or you want to find out that whether it is the same image which we want to get in the output. In the convolution, see, apart from that limited cases where you basically use for the pattern matching, everywhere we use basically the convolution. Even see, we whatever you would have heard it, we use basically a different type of filter that the pulling, yes, pulling, etc. These are basically the concept of the deep learning, machine learning. Definitely, the convolution has been now, but initially, actually, it started from the image processing, or even started from the signal processing, actually, from the linear system. So here see you can see the operation. For example, some origin is there. For example, this origin is there. This is one dimensional. Only it has been shown here so that you can understand this operation. Otherwise, image is basically the two dimensional. What has been shown here? Let's see. See this origin is there. What is its length? 1, 2, 3, 4, 5, 6, 7, 8. Right? For example, we want to find out the correlation of this of this f, this linear one with the w. So what will happen in that case? In that case, see, it is simple thing is there. So for example, this is, so what do we do? First, when we will multiply, we will multiply that 1, 2, 3, 2, 8. This is length of the 5. So when we will multiply, so we will multiply in such a way that the first element of the this F will coincide with the last element. This 8 is coming here. But since 8 is coming here, see what will happen to the other values? What will happen to the other values of the W? So what do we do to facilitate the sum operation? We basically assign the zero. We call this process as basically as the zero padding. It means we basically add the zeros in the beginning. Add, or we better say we append the zero in the beginning. How many zeros you append? Definitely as many zeros which can take care of the other element of the mask. So this is 1, 2, 3, 4. 1, 2, 3, 4. So 4 zero padding. So 4 zero padding that we do here. In the same way, this 8C, what do? You will shift it gradually, bit one by one. What will happen? It will slowly you will shift toward after one shift. After one shift, what will happen? This 1 will come here and this 8 will shift. Everything will be shifted toward the right. Now again it will be shift. So after fourth shift, what you can see? Fourth shift means it is 1, 2, 3, 4. 1 will come here. Thereafter 2, 3, 2. 2 will come here. And exactly 2 is below the 1. So that we can see here. In the final position, in the same way, what will be the last position? Last position will be the one where this last 0 will be there. Last 0 of F will be there. So this is their F1. Again, we need to append the zeros. How many zeros? 2, 3, 2, 8. So this we will append it. So again, it is a 4 zeros. So when you have to do the operation, so you need to append the zeros, or you need to do the zero padding in the beginning as well as in the last. Now, what is the result? How do we calculate the result here? We calculate the result here basically by calculating these values. We see the first position, the initial position. This is the one in the C. What is happening here in the C? We are multiplying here. 1, 2, 3, 2, 8. We are directly multiplying and summing. So what value is coming? 0. After the first shift, again see when you will multiply all these elements, 1 with 0, 2 with 0, 3 with 0, 2 with 0, 8 with 0. Again we will get basically 0. Then we again shifted at the third time. 1 will come here. 1, 2, 3, 2, 8. 8 will come under the 0. Again it will come 0. Then thereafter we will again in the fourth shift. The fourth shift, 8 will come here, 8 will come below the 1, and the other values, so we will get the value 8. Thereafter 8, the 2 will come. So you can see this position. This 2 will come in the fourth shift. Sorry, that was in the third shift. So now it's come in the fourth shift. It is 2. So this is the 2. Then in the fifth one, 3 will come. Then in the sixth one, 2 will come. Then in the seventh, it is 1 will come. So in this way, we will able to get the full correlation result. Is it understood? Any question? So now what do we do? So this is our full correlation result. Now, what is its basically length here? length we again check out that its length should be same as the original length of your signal. So 1, 2, 3. So what is this length? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. What do we do? To get in the same length, it should be of the same length. Again, we will crop it. We will crop the first two element and the last two element here. And so this way we get, this is basically the output of the correlation. Correlation of this one dimensional mass with this one dimensional state. What about the convolution? In convolution also you can see that you take the origin and after taking the origin, then you, but as we discussed in the last slide that in convolution it involves the flipping vertically and horizontally, but since it's a one-dimensional signal only, so what will happen that this 8 will be flipped, this 8 will come here, this when it will be flipped, so 8 will come here, then 2 will come, see 8 will go on the most left hand side, then 2 will come, then 3, then 2, then 1. So again, see, just we have to do the flipping and thereafter we need to do the multiplication. So then again, so what you will do, again you will multiply with the origin and when you will put it, the first element near the, this is the right hand element near the first zero, so you will get it. You need to padding also. We are doing basically the padding here. So this is the zero padding. So the question is there that what will be the effect of correlation and convolution in the image? See, it will actually depend upon that what is your mass. See, one direct impact if you are seeing there that when you are taking correlation and convolution, so whatever values are there, right? They are coming actually, see, they are based upon the what value does contain in the mass. So it depends upon the mass. We will see it. These things will be gradually open that how do we decide the mass to make a impact. So thereafter, what do we do? Thereafter, we shift it. We shift it toward the right. It, we will further shift it. And what will we get? We will get this output. But important part, correlation and convolution both have the different output. It's a relation between two images. The mask is not actually an image. Mask is not an image. It's a where you see 3 by 3 element. Can't say it's an image. On image, its work actually gradually upon the whole image. Can't say it's a correlation. Yes, if both the things, if two masks are there, both are of the same length, then we can say. But otherwise, you can't. But yes, if somebody asks me, for example, we use the some functions like in communication, autocorrelation, etc., cross correlation. There we say, that whether is there any whether is there any similarity, etc. But in this case of this image processing, when we are dealing it, there you can't say that it is basically similarity between this mask and this image, right? If two are of the same level, same size, then we. So what do we do? So we have also able to get the result, and so we are able to do the operation, one-dimensional operation of the mask with the signal, and we are able to notice that both the results are different. Right? So what we are saying, they are functions of the displacement. This is the, so any question. This is important that we have learned basically the basic operations of correlation and convolution. In engineering, this is the required that you first you know that actually the goal, what do you want to do, and then to do it with the help of the your techniques, your mathematics, algorithm, and then you finally evaluate whether the desired impact has come or not. Is it understood? Okay. Can we go any, because this is the base, correlation and convolution, or the base of the filtering. Okay, so if no, it is clear, then please mention it. So I would be confirmed that yes, you are. So now coming to the parts, the convolution and correlation. In convolution, so what is basically in the convolution? Convolution, as the one question has been asked, what is basically the impact? There are many impacts. Even whole subject is there of knowing the impact of convolution, depending upon the different type of mark. So what is the impact? See, one of the impact is basically filtering and edge detection. You filter it. Filter means basically you are able to find out some particular values when you are applying the mark. Edge detection. You will also use very frequently this convolution operation for the edge detection. Another thing, the output gray level at a pixel. Again, see, we have come the output gray level at a pixel is the weighted sum of the gray levels of pixels in the neighborhood. So see what is actually happening. Only see this thing is happening in this case that it is basically the weighted sum. When we are saying it is a weighted sum of the gray levels of pixels in the neighborhood. Here the kernel elements. What do you mean the kernel elements are taken left to right, top to bottom? What do you mean by the kernel? Kernel is basically the same thing which we are calling the mask. Kernel and mask are the same thing. Kernel and filter are the same thing. What we are saying that they are taken left to the right, top to the bottom. Since actually we have taken only the one dimensional, so that's why we have seen it only the left to right. If it would be the two dimensional, then what do? We move from left to the right and top to the bottom. Let's see. Image elements in the neighborhood are taken right to left, bottom to top. So when so either see, because we are moving basically the mass, so this sufficient for the operation. But if somebody say no, I want to move the image element, which is the more difficult way, then you do it in this way, that you move right to left and bottom to top. But normally we move the kernel because it is smaller in size in comparison to the. Now coming to the part correlation. In correlation is basically you do the feature recognition. Kernel is now called basically template. Template is basically, if you recall, see, for the what template is like the pattern. Find out the whether this template is present in that particular signal, whether that template was similar or not, etc. These type of. Algorithm is the same as convolution, except for the pairing of weights with pixels. Kernel elements are taken left to right, top to bottom. It is the same thing what we are saying. You can get correlation using the convolution algorithm by rotating the kernel. Disadvantage sensitive to changes in the. So now we will see the more mathematics so that we can understand. As we see discuss basically that in the spatial filtering, what do we do? We basically do the smoothing. In a smoothing, basically, we do the low pass, and low pass, what do we do? It is, as we discussed it, it is basically the linear filter. It is used for the blurring and noise reduction. So how does it work? Here the value of every pixel is replaced by the average of the gray level. So how does it come in picture? For example, this is the example of the one mask. But remember, this mask is there of the size 3 by 3. You will uh, the researcher will basically put the value, the central value of this mask, this one, upon the image pixel where you want to act upon. If, for example, the image value are present, then you will directly multiply. If they are not present, then what do? You do the basically the zero padding, right? That way we are able to do it. And then this is one type of C standard average filter. This is the weighted average filter. Here we observe that we want to get the different type of weights, right? What we are doing in both the cases, we are normalizing the value 1 by 9. We are, see what will happen of this putting this way, we will directly able to see the impact in that range only, right? Whatever it range is there, that will be remain same when we will normalize it. In the same way, in this one, when weighted average is there, so what is the value? If you will add up here 1 to 1, it is 4, and then 6, 10, it is 12, and then it is 416. 1 by 16 into this one, so then we will able to get it. So this is Python code is written. If you in Jupyter or in Google Colab, you can write this code. Spatial filtering, so now we take up basically the image of size by the 4 by 4 pixel. What were we doing? Here somebody say that can you apply the mask and can get the value? Yes, we can easily do it. So what we are doing? So on which element we want to put it? So here if you observe that we are applying on this 94 pixel. How are we applying it? We are basically applying it. So this is the one. This is the where this one will coincide here. So 1 into 94, so that's we have written 110. If 1 will come here, here why 1 will come here why 1 will come here also 1 will come. So when we will multiply this thing, see 110 into 1 plus 120 into 1 plus 90 into 1 plus 94 into 1 plus 98 into 1 plus 90 into 1 plus 91 into 1 plus 99. And then finally, we are doing it, we are dividing it by 9. Parvesh has asked one question, so let me check. So 1 by 9 matrix and 1 by 60 matrix are two different. Yes, definitely. They are the different filter. They are both the actually the linear filter. One is basically the mean filter. Sorry. One is the standard average filter, another is weighted average filter. Yes, they are two different filters. Sojan is asking, is any dimensionality reduction applied here? See, dimensionality reduction we are not bothering till now. That will come later. That's how we are getting this value. If you will do it, weighted average can also be called as Gaussian filter. Yes, the Gaussian filter actually we call basically the standard one, standard average. So weighted average, what you are doing, you are multiplying under 10, etc. Then you will get this value. So this is what we are getting. What we are getting in the standard average filter, instead of 94, we are getting 98.1, and in the weighted average filter, we are getting the value basically 97.8. So this is the way the impact of the different mask on the pixel value of the original image. But as we discuss, what is basically the impact? What is the impact of this spatial filtering? The impact here is simple one, that it smoothens the image. What do you mean by smoothing? Smoothing basically you level the difference. Every part here in surrounding it will remain same. It's leveling out, leveling out. So here we can say that it was the original image was there. Then what did you do? You basically applied the smoothing. Smoothing means basically you take up the some 3 by 3 matrix or 1 by 9 or 1 by 16 and then you apply it here. This is basically the image. Then you take up the 5 by 5. Somebody said, no, I will check the different sizes. Okay, you can try out. So this is basically they are taking 5 by 5 means, then you are taking 7 by 7, then 15 by 15, then 25 by 25 mask. And what is the difference? Are you able to see the difference between these images? All have been basically operated by the same type of standard average mask. The only difference is there, it is in the size of the mask. Can you tell? In case of 5 by 5, it is 25 element. Yes, blurriness. So previous telling it's blurriness. Other one. Any other thing? Yes, absolutely. It is basically blurriness. Why the blurriness? Because see, when you are taking the bigger size of basically the average filter or the mean filter, see the all the values, all the surrounding values will come into play role at that pixel. So what will happen? So it will smoothen out. That's why the smoothening, the level of smoothening will be far more when the size of the mask will increase. But remember, is there any disadvantage? Yes, one disadvantage is there that you miss the loss of detail in that case. So in the same way, so here what we are showing, see here you can see, for example, some bird is there. You apply basically 3 by 3 smoothing filter and you get this smoothened image. And then thereafter you again original image. You have also applied the smoothing filter and there you are able to see the uh, as some better image, smoothened image. So this is the way to use basically the different type of spatial filtering in the smoothing. In the same way, the mean filter is also used to hide the identity of a person. You would have seen these type of pictures in basically the newspaper, and the TV. Then, for example, some criminal cases has been going on, and we don't want to reveal the identity of the either party, that is a criminal or it is basically the committer. So here the input image was there. Here you apply the 11 by 11 kernel, and here you apply 29 by 29 kernel. See, now we come to the part non-linear filter. So what happens in basically non-linear filter? See, in non-linear filter, it is not simply the multiplication, it is something more. So that you will see. So in non-linear filter, many types are there. First, we take the median filter. So what happens in the median filter? In median filter, it replaces the value central pixel with a value determined by the ranking result. Edges are better preserved in this filtering. So how do we do it? So it has been told to you that will we will use basically the non-linear filter for extracting the different type of things. So how do we do that? You can see here. Each pixel in the image is considered. First, neighboring pixels are sorted and original values of the pixel is replaced by median of the list. Right? So we will take up the example here. For example, this is a image of 4 by 4 pixel, and here, so when you do that operation, that median filter operation, what will be the answer? The answer will be basically 95. How it is coming 95? Because when you will multiply 1, 1, 1, 1, keeping in the center here. So what you have to do in the median filter, as the name suggests, basically need to put the values in an increasing way. Once you have put it in an increasing way, there you will find out the 9 elements. So when you are taking these basically 9 elements, so you take the in between element, you take the median element, which is the median element. So first we calculate the number of the pixels 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 is there. So the middle element we were interested in the fifth one. The fifth one is there. So some pixels are there in the ascending order. So what do? We replace the original pixel value by the median. When it has come 95, so we will put here 95. So it is very less likely to generate the error also. So what do we do here? See, in non-linear filter, another filter, see, it is basically to use the remove salt and pepper noise, right? What is the salt and pepper noise? Salt and pepper noise is basically, salt is basically white and pepper is black. In the event, it is basically kali mint. What we are saying in this part, so this black and white spots are there. So here you can see this is basically the your salt and pepper noise, and when this is there, so when you will do the averaging, what happens? Averaging will basically bring the impact of the surrounding, will bring the impact of the neighborhood. So you will get this type of image. See, it is small change in pixel. Does it in the media? There will be. See, it depends upon what is your mask. For example, it totally depends upon the value of the mask. What we are saying here in the averaging part, see if you can see that the noise is already our picture was better, and it has further noises have been added when averaging was done. So the best way actually in that case is it is basically the median filtering. When we have taken the result of the median filtering, you can see in the fourth image it is far, far better to be in comparison to the first image. So now coming to the non-linear filter. In non-linear filter, see again we take up the another example of salt pepper noise. In salt pepper noise, again see this matrix is given. In this matrix, again you can order it. Once you order it, so what you will get, which block we are taking, we are basically operating upon this pixel, this 0. We can change the value of the mask and median filter to get that absolutely. The mask is totally in our control. We will design the mask. Normally, see in the linear filter, it is Gaussian, it is basically all the values are one. That is the standard one. So in the non-linear filter, again, when you apply it, in which region you apply it, you can see here. So here you can see again the 9 elements are there. It is 1, 2, 3, 4, 5, fifth element. 6, 7, 8, 9. So here they have basically shown it. So when you show it here, so the value 204 will come. What will you, and if you take the mean value will be, when you will add up this thing, it will be 181. So you can compare it that how much difference is there in the median filtering or the non-linear filter. So again, we have taken it. See, whenever it is a salt pepper noise, it is always difficult to correct the things by the mean filter. So what we are using basically the median filter. So here see we have put basically the programs here. In the program see again as you people can see here some small programs are there. Even you can note it. Import CV2 as we have done it. Import NumPy as NPy. So in the Python you need to basically download all the this libraries, and then after library you use CV2 NumPy, and then you are calling the function of the CV2 image read that brain.jpg. This is basically your brain slice, and then median equals CV2 median blur. So when you calculate out the median, you can calculate it using this function, then you compare it, and then after uh, comparison, then we finally add the compare and then concatenate. So, and finally, we will again see the image, and so this is basically the overall impact of the image of using the non-linear filter. Another thing, see, where do we use basically the non-linear filtering for noise reduction? So it has been shown here, some electronics chips, the system is there, original image, X-ray was there, it was corrected by salt and pepper noise, and thereafter it is noise reduction with 3 by 3 averaging mask that we have done. And then we have done again the noise reduction with 3 by 3 medium filter. That you can see that it is there 3 by 3 medium filter, and people have tried to get the reading innovative, right? So now coming to the part sharpening, basically spatial filter. So what do you mean by sharpening? Sharpening means basically for some boundaries there, I want to detect that boundary. So that is possible. So what we are saying that aim is to emphasize the transitions in intensity. We will use basically the Laplacian operator, use the unsharp masking and high boost filtering. We will also use basically the first order derivatives for non-linear image sharpening. That is basically the gradient. So gradient plays a key role. First order derivative of one dimensional function is basically the difference. So see, the question arises, how will you find out this gradient? How will you find out the derivative? Derivative things are a bit simple to do here. You simply take the subtraction of from the neighborhood. Which neighborhood? Which is basically the x plus 1. X plus 1 is basically toward the right hand side. So here what we are seeing that the second order derivative of fx. So what would happen when we take the second order derivative? Then see fx plus 1 plus fx minus 1 minus 2 of y. That we can do here. So what is this happening in this filter? It is basically sharpening a spatial filter. And sharpening a spatial filter, here we see, for example, these points have been plotted, and when these points have been plotted, it is we have drawn the analogous image strip where all the values of the gray level will lie there. So image strip is there 5. So what has been going in here? So if you see here, this is 5, this is 5, this is 4, this is 3, this is 2, this is 1. In the same way, if you go there, you can continuously uh, fill all the element, and that's all. So We are saying first derivative, again we are stuck with what is basically the first derivative. So first derivative is nothing basically as we have seen in the last here, that it is fx plus 1 minus fx. So it is the later value minus a small value. So this here 5 minus, so 5 is there, it is 0, and 5 minus 4, it is minus 1. So 4 minus 3. So what we are doing, it is fx plus 1 minus fx. So fx plus 1. Here this is the later one, 4 minus fx. So it will be minus 1. Then 3 minus 4. It will be minus 1. 2 minus 3 to minus 1. So in this way, we can complete the image strip here. What is this? This is basically ramp function. What do? We have calculated the first derivative, we have calculated the second derivative, and that is all. So here it has been shown here that the intensity shown here, intensity transition has been shown here. So what you notice in the differential part, that your intensity will be maximum, your value is maximum when you are basically use the linear filtering. Linear filtering, against it is the same thing, 5 minus 6 minus 1, 4 minus 5 minus 1, 3 minus 4 minus 1, 2 minus 3 minus 1. In the same way, how we can calculate the second derivative? Second derivative, see, we can calculate, see, minus 1 minus 0, minus 1 plus 1, 0, 0. So second derivative is basically we are subtracting the value from the first derivative that we have done. Scan line represents the pixel value. The scan line we see that we are saying that is basically the intensity transition line. There it represents the pixel value. Yes, definitely. This is scan line here. This is represents the pixel value. So what happens when we do basically the sharpening of the spatial filter? We applying the first derivative basically get the thick edge to boundary. You are saying, see, what do we get? We basically get the boundary using the first derivative. When we use basically the second derivative, then the double edges of 1 pixel thick. What we are noticing here, that observation and inference, that along the ramp, the first derivative is non-zero and second derivative is non-zero at the onset and at the end of the ramp. Which you are saying ramp? Ramp you are saying here in this part. This is in the ramp size of the. So what is the purpose? The key purpose and the key difference in the that first derivative, it is a thick edge. In the second derivative, when fine details are there. For example, some boundaries are between very thick one, very broad one, but some are very, very thin one. So if you want to bring out that thin boundaries, then in that case, you use the second derivative. So at isolated noise point, second order derivative has much more response than the first order derivative. So what we are saying is basically when you have the noise points are there, then you are easily able to extract out the information using second order derivative. Ramp and step edges has opposite sign. So about the inference basically first order derivative produce thick edges, whereas second order derivative we have produced much finer ones, as we have discussed it. Second order derivative has strong response, fine detail. So it depends upon, see, if your image, for example, your facial image is there for facial expression, etc., then you use a second order derivative. Finer details, etc. Because see, in histogram, what did we do? We basically use a high contrast approach. There the fine details come up. Here, what do we do in spatial filtering? Here we apply the second order derivative. Second order derivative produces a double edge response at ramp and strip transitions in intensity. So what actually happening? It is happening that they are basically finding out the change here. When you are taking the difference, fx plus 1 minus fx or fx minus 1 f1x minus 1 minus fx. So in that cases, we are getting the sign change, and the amount of sign change basically indicates that it is the how much intensity is there. SOD is basically second order derivative. So I think we can just take a break. 5 minutes, right? We will come back. If you have any questions, we will just discuss. Right. So, any question regarding anything regarding the what we have discussed regarding the spatial filtering? So now see, coming to the part here. So what we are saying here in the one line, we are basically sharpening. Sharpening means basically we are highlighting the boundaries or the edges using the derivative. If your edge is thick, then first derivative is sufficient. If your edge is thin, then we go to the second order derivative. So in mathematical, see, mathematics definitely you would have seen it. See, we call it basically the Laplace operator, right? Laplace operator. It is, what do we see? For example, this function is there. What is this f(x) of y? This is on the two position. And so delta operator del square equal to del square x square, del square f upon del y square, this partial derivative. So what does this mean? Because your image is basically a discrete function. It's a discrete function, so it is basically very simple one, fx plus 1y plus fx minus 1y minus 2fx. In the y coordinates, what is basically it is saying? It is basically that when we are moving the left hand element, the right hand element, and then we add up and then we subtract the double of that value. So del square upon f square, it is fx. This is, and in case of the y, you take the upper column, you take the lower column, and then you add up and then you take the double value of them. So overall, see, if you want to calculate the del square f, so what does this mean? It means that we are adding all these four values. So that's why, see, from 1 and 2, we are adding both these values. It will lead to the minus 4x. So now we see the basically the different type of filter here. So it has been shown here. So what is this? This is filter mask. So here when we are saying it is, see, till now we have taken the average filter, right? Average filter that we are taking all the one value. But when we want to find out the difference, we want to basically this derivative, then we use that type of filter. Please notice it here. Here the value is minus 4. Here 1 is there. In the same way, if you feel it that even you are able to take the effect of the other neighborhood also, then you take the -8 and you take the 1 here. In the same way, another way we can take it that you can take the 4 here at other values at -1. In both the cases, it will lead to the sharp. Another way to implement here that you take this one as 8 and other values as the -1. It is all about the neighbor. So it is the same thing. Either of the way you can implement. So image sharpening in the way of using basically the Laplacian, it is gx of y. So this is basically the final image. So how do we get it? The final image is this one. When we will add up the original image plus that derivative. And how much? Go back to the slide. Which slide? Where are you? This one? Pravesh, where you are finding difficult? in this slide or here? 3.66 equation. Let me see. Okay, 3.66 equation. Filter was used to implement the equation. Okay. So this is the only this. Actually, see what we have done. We have taken this slide from the book actually. Gonzalez, that's why it has been. This equation is there. The second order isotropic derivative operator. This is Gonzalez. This is the basic book, right? So this is the case here. So, so now we are. What is this GXOY? This is the sharpened image. This is FXY the input image. What is really important here? See that it is not the GXY is not coming from the only differentiating it. It is coming after adding with the FXOY. And that has been shown here. What has been shown here? So if you do the C equal to -1, if you use the filter 3.7 A or the B, and you do the +1 if either of the another two filters are used. So remember, there are many ways to implement to get the image. Beauty. Now we take the example that how does this operation take place. First, we check out the sharpening first derivative. So this is basically what we are doing. We apply the following Laplace on the highlighted pixel. So here what we are doing, again it's a image and we are since this is our mass. When we are taking this one as a mass, what we are doing, again we are multiplying 154 multiplied by 4 minus 158 minus 158 here. This is minus 158 here, minus 158. Either minus 156, we will get this value and we will get the minus 14. So the value after filter we are getting it as a minus 14. We call this resultant image as a sharpened image, filtered image. But remember, this is minus 14 is not the filtered image. Which one will be the filtered image? Can you recall? Just we have discussed it. But what will be the value of the filtered image here of that pixel? Anyone's guess? Anyone's idea? Anyone's idea what will be the filtered image? See, I repeat the question. See, for example, 154 is basically this original pixel value. When we will apply the first order derivative, what will be the resultant pixel intensity? So where are you find? See, again, I repeat the question. See, this is basically this image is there. This I want to apply the Laplace. It is 50. Thousand is saying 50. Any other answer? Good, at least. You are coming with some answer, good, applying. Does everyone agree with 50 or some another answer? Okay, so see, there is no Pravesh is saying 140. Yes, if you see, really recall, what we are saying, we are basically adding the image here. Gxy, fxy plus c delta square fxy, right? So we have done the same thing here. So what we are doing in this thing, go to the this diagram. So this, see, this is basically my. We are here, what we are doing. See, when we are doing this operation at the first order level, so what we are doing, 154 into 4. We are doing all these values, so we are getting minus 154, and this 154, this one, and what we are doing, then we will subtract it, because it is the original pixel value plus this value. So it will basically lead to the answer and that is 140. Correct? It is not 130. That's why I want to highlight it. Is it clear? Minor change here. Is everyone with me? Yeah. Please correct it, right? This. So now if we apply the second derivative, so what would we say in the second derivative in this one? Second derivative means again you will multiply this value. So when you will, but please notice it here that when you will apply it again, so how you will get 154 into 4, 158 minus again this is minus 14. And now what you are doing, the second derivative, you are applying Laplace, you are applying, see, this function, minus 14. So this is minus 14 multiplied by 4 minus 10 into the original pixel value. Yes. What we are saying, it is minus 14 minus 6 multiplied by minus 4 minus 10, here you will get minus 6 plus 6. Here you will get minus 4 and here you will get minus 10, right? When you will multiply this one upon this one. So are you aware, see how you are? So this is minus 74 and minus 150, this is 80. But have you understood, see how this block has come? Want to highlight upon this block. Is it clear? This is not. Are you able to understand? See what we are doing here, actually, if you notice it, that for example, we have calculated the value minus 14 after the first derivative. In the same way, we need to calculate the value for the other pixels also. You are able to apply the second derivative when you are able to calculate all these values for every pixel. So what will be its meaning? It means this 4 will be multiplied here for 158 and this 1 will be multiplied here minus 1. So what will we get? 158 into 4 minus 156 minus 154 minus 157 and minus 155. So that you can check what you will get here. 3, 2, 5, 4, you will get 10. Are you getting it? When you will apply here, so when every time on 157, when you apply, you will get the value 1. This same filter. So after applying this filter, after applying this mask on the every pixel value, here you will get these values minus 8, 10, minus 2, etc. And thereafter, when you will apply, what you will apply this same thing, same filter you will apply here. So the value after second derivative filter, that is minus 74, and minus 74, then you will do it this one. So you need to do how many calculations? So you need to do the 8 more calculations, 8 more multiplications when you want to. So thereafter the resultant value will come, and then only when you will get this matrix, and then you will multiply it, and then finally second derivative, and then you will add up with the original value, and then it will come 8. What is basically the thing here, that in the first derivative it is 140, in the second derivative it is basically the 80. So major changes come. So that is it understood? Can you proceed, or any question? Very important for Laplacian operator. So I hope is it understood. Is just knowledge. What do we so after see, if we really want to see the impact, see what is happening here, that if it is the original signal is there in this way, for example, on the y-axis it is basically the amplitude, intensity, amplitude, and on the x-axis that is basically the number of the pixels, that these pixels are there. This is their order of the pixels. Then see what happens when we apply basically the uh, filter. When we apply the masked average filter, we got basically the blurred signal. What are you getting in the blurred signal? In blurred signal, if you are seeing, see there is a smooth change. The values are average out, so it is basically a smooth out. And then it is the unsharp mask and the sharpened signal. In the unsharp mask, what you are able to notice, that where the change is there, that part is highlighted, that part is, that edge is clearly bring out, that you can see in this diagram here. Again, in the second order derivative, again what we have done, it is even further highlighted here and here. Definitely, from in the PPT you will get it. PPT we have already provided for the others one also. Definitely, you are going to get it. So can we move further? So these are the key things. What we have done basically, we have first we get to know that what is basically the spatial filter, how is it important. Thereafter, you basically uh, get to know the mathematics. How does it operate? Thereafter, what we see, we took up the specific example and then we noted down the different values. But overall, see, we want to see the impact. That what is its impact upon the image intensity that we are finally observing. Yes, I already told you that one thing, one key mark, benchmark in the image processing, that what is the impact of any operation upon the image. If you are able to get it, then it is sufficient to understand that. Another image, see, for example, this is very, very famous one in image processing that is basically called the cameraman image. Cameraman image, see, so what you are doing here, see, here, when you apply the Laplacian sharpened image, basically first, so when you have applied the derivative, so this, for example, it's like a minus 14. When you have applied the minus 14, it is this one. Only edges are visible. Are you able to see what a wonderful beauty? It is there. All your edges are able to get. And thereafter, if you add up this sharpened image with the original image, what will you get? You will get this image. Can you tell me, is there any difference between original image and Laplace filtered image? Are you able to see any difference? More brighter noise reduces. Yes, absolutely. See, what is happening actually, whatever the different part is there, whatever the difference is there, wherever the edges are there, that have been actually demarcated out in the sharpened image, right? Sharpened image, they have been basically demarcated out. It's basically like the sketch. For example, when you prepare a sketch of anything, it is like this one. And as soon as you add up it here in the original image, it is very clearly coming. So whatever it is the difference, whatever the difference. So that's why see, if you are able to see here, you are very clearly able to see this strips here. This strips at this stand. And another here, you are more able to see the equipment detail, etc. So see, actually these observations became the then final basis for deciding these operations of the filter. That is the beauty of this image processing. That whatever operation is there, you are able to see its implication uh, with its operation upon the image. Image sharpening based on the first order derivative. So what we are saying that it is function fxy gradient of f at coordinates is defined as this one, grade f equal to gx dy del f over del f. Magnitude of vector denoted as this one equal to magnitude is gx plus gy square. So if you recall, see, this is basically the again the Manhattan. It is this city distance, whatever we are taking it, and these are the another ways to take basically the derivatives apart from the Laplacian order. So we also call this one, for example, 3 by 3 region of images there in this case, and we somebody wants to apply the Robert cross gradient operator. Robert cross gradient operator, it can be -1, 1, 0, 1. It can be -1 to 1, 0, 1 in this way. And apart from it, you can also apply the Sobel operators. Again, see the see what we are saying that there is no only a one way to get the first order derivative. It started with the Laplacian, but thereon it was extended with the different type of operators because of their specific significance. Need to check out. We already see these functions are defined in the Python, etc. There you can directly use it and you can check out that which one is getting proving better one on your image. What is this Robert cross gradient operator? This is here, this MXY. This is this basically mod is there. Mod this one and this one. Mod of Zn minus Z5 plus Z5. Zn minus Z5 plus Z8 minus Z6. Here it has been shown. Cross gradient. Sobel operators it has been shown Z7 plus 2, Z8 plus Z9. Here it is double one. It is minus Z1 plus 2, Z2 plus Z3. In the same way, it is Z3 plus on the column wise also it has done 2 Z6 plus Z9 minus Z1 plus 2 Z4 plus Z7. So in this way, the Sobel operators can be. So it is basically image sharpening based upon the first order derivatives. It is basically Roberts say. Roberts says here you can see that it is much more better than the Laplacian. It is same cameraman here, and it is the Sobel age. It is as detection is there. In another case of the image sharpening, here this filter is used. Actually, it is the first one, same the Laplacian. Here, when we applied it, we were able to see this images. It's like basically the film of the original image. But instead of here, we find it that when we increase the magnitude instead of 8, when we give the more weightage to the 9, see there it is more better. So depending upon the value, we see it that it becomes further, final image becomes further noticeable and better to even see if somebody said no, or why should I limit to the 9 only? We can increase to the 10 also. Yes, you can increase to the 10 also, but at the 10 level, you see then it has become more brighter actually. Right. So instead of it here where things were more appropriate, here things are not that much appropriate. So there is some optimum value when you are applying these first order derivatives. So this is where we concluded about the spatial filtering, and we move to the another topic in the filtering, that is basically the frequency domain filtering. The frequency domain filtering, here we applied that in image frequency domain filtering. See what you do basically first you convert the image into a frequency domain. How do you convert it into, or you take basically the spectrum? And how are we able to do it? We are able to do it basically with the help of the Fourier transform. Fourier transform actually allows which type Fourier transform? 2D Fourier transform. And then you will basically pass it through a low pass filter, you pass it through a high pass filter, or in some cases it may be a band pass filter also. What is the key thing? The frequency domain filters are basically used for smoothing and sharpening of an image by the removal of high or low frequency component. Sometimes it is possible to remove very high and very low frequencies. They differ from a spatial domain because here see the frequency of the image becomes important. And then all the enhancement procedures are performed on the transform of that image. So what is basically the concept of the frequency in the image? Are you aware? Any idea? So see, bringing one concept is fine, but its actual implication, what does it mean? And what are we supposed to get when we are applying a low pass filter and high pass filter? This one. And here we will conclude also for this session. But before it's what is basically the idea. What is frequency? What does low pass filter give? What does high pass filter give? So this is thought for you, right? To think it while coming to the when we proceed further. You see these basic concepts that knowing the frequency, knowing this derivative, etc. with its implication on the image. That we really want to get. Because once this is clear, then we will able to understand what is low pass, what is high pass filter doing, etc. etc. Here we conclude our this session. If you have any question, I have one question for everyone. This frequency part. So will high pass filter allow high frequency signal. See, that is fine, but what do you mean by the high frequency base signal? That is right. To think over it, let it, whatever you know, whatever you have learnt it, try to find out it. So thank you. Conclude it. Pixels intensity having high frequency, but what does it mean? Definitely having high intensity. In common layman words, what will you say? So thank you. We, I think it's better to think